Welcome to Hot Chips 23. Keynote 2. Challenges of building personal robots.
All right, good afternoon. So as processors have attained higher computational capabilities, we're seeing that designers are finding new applications for them. And what we're going to hear about in our next talk is an area that's receiving increasing interest, and that's namely the merging of mechanical and electronic systems in robotics. And this goes beyond the traditional applications of industrial robotics, and we're talking about personal use. So I'm pleased to introduce today's keynote speaker, who will be talking about just such a robotics company, and he'll be talking about not only the innovative hardware that they're developing, but also an interesting open source model for developing the challenging software for these types of robotics. And I'm told that we'll have a live demo here also. Steve Cousins is president and CEO of Willow Garage, which was founded in 2006. Prior to joining Willow Garage, he was a senior manager of the User-Focused Systems Research Group at IBM Almaden Research Center, which is known for its Human-Computer Interaction Research Lab. Earlier, Steve managed the Advanced Systems Development Laboratory at Xerox PARC. Steve has a PhD in computer science from Stanford University and BS and MS degrees from Washington University. So, Steve?
How's that? They said if I keep talking, they'll figure it out. Is that better? Okay, good. So thanks for having me here. I thought about, Hot Chips is a conference that I've seen advertised for a long time. You're hearing me here only? Oh. That's going to be too bad when I have a robot to wander around to see, but okay. So thanks for having me here. I've read about Hot Chips conference for a long time. I was at Stanford and I started getting emails about this conference. And I'll try to show you what we can talk about in terms of what's needed in robotics. That's what I'm going to try to get across to you today. But also I want to show you what's cool and what's state of the art in personal robots and a little bit about what personal robots is. Let me start though by going back in time a little bit. This week, earlier this week, George Duvall, who's the inventor of the robot arm, passed away. He was 99 years old. And here's a clip of from Johnny Carson. Yes, he's actually smoking a cigarette on TV in California. And so you can sort of date this that way.
And he's got a wild machine to demonstrate tonight. Would you welcome Joe Engelberger? Joe? Get out here a little bit. What do you call this machine, Joe?
It's called a Unimate. It's an industrial robot. It does the work of a man in the hot, the hazardous, the tedious jobs like die casting, forging, paint spraying, anything repetitive. There's about 65 of them out right now, and we're making 20 a month.
And they rent them out to companies for particular kind of work, right?
Well, we sell them or we rent them. If you haven't got $20,400 ready, why, we'll rent them to you for $2.50 an hour.
Sounds reasonable.
So you get a sense, this is a huge mammoth device, and one of the things that's noticeable on the Carson show is that they have to pretty much stop talking when the robot's turned on because they can't hear over the noise. the thing is massive. It's got a pretty cool workspace, and they were able to do putting on the 1960 on the Tonight Show, putted the ball into a cup, and they were actively talking about how that robot was going to replace people's jobs, and they had it do a band direction thing, and as though the band director is always on Carson was getting kicked off. That's industrial robots, right? And that's been going on for about 50 years, and has had a fair amount of success. We've basically saturated the stay in one place behind a cage need for robots in factories. There's now the opportunity to have robots that move around outside the cage around people. There's a big national robotics initiative that was just announced by Obama a few weeks ago that is about trying to get us competitive. They call it co-robotics, so a robot next to a person doing a task more productively, so adding productivity to the workforce in order to try to get manufacturing jobs back here. And I'll show you a lot of other examples of robots along the way. But what we're talking about now is personal robots. And for personal robots, let's see if I can click to make this work. That's, I think, the next 50 years. The past 50 years has been successful, and it's kind of hit up to a point. But personal robots have to get out, and they're no longer in an environment where you can fixture the environment in advance. You have to look at the environment and say, hey, there's people wandering through here. They might just leave a backpack or a pair of shoes in the middle of the floor, and you've got to remember to avoid those things or be able to avoid those things. I can move now? Oh, that's great. I feel much better. So here's an example of a wide range of different personal robots. I'm taking this from a point of view of Ross. So when I usually give a talk, what I talk a lot about is the robot operating system, which is an open source platform that we've been putting on our robots, and lots of other people have put on all these different robots and many more, to try to make it so that we can accelerate the future of robotics and get it here faster. You can see the range of robots here, and I'll show you a clip. But before I do that, let me show you sort of the canonical personal robot. This one, I call this this is called the PR1. It was actually named after we started building the PR2, and they said, what are you going to call that one? We'll call it the PR1. But here's a robot that's doing a whole bunch of human scale tasks. These are all being done under teleoperation. This was invented here at Stanford, built in Ken Salisbury's lab, and by those two students that you saw in the video, Eric Berger and Keenan Weierbeck. And the idea was, let's get a robot that's facile enough that it can do what Rosie could do in the Jetsons, but without the attitude, right? If you remember, Rosie was kind of jumpy and could do a lot of stuff. So there's actually a clip. I don't know if it's in this video clip, but there's a nice clip where they have it turning on a Roomba, so you have robots working together, and the Roomba doesn't actually start, and so it picks it up and puts it in the trash. Kind of not making me popular at iRobot, but. So this is cleaning up a room. Again, this is under teleop. So there's somebody in the same room sitting with two phantom arms, picking up, or basically moving the arms around. And as they move their human arms, the robot's moving its arms. And so they were demonstrating that the hardware is capable of doing these tasks, taking a lid off a beer and so forth. So, and that was a really lazy grad student, right? I mean, he wouldn't even reach forward. So this is circa about 5 years ago. Right? And this was pretty much, in terms of robot hardware, state of the art, in terms of the mechanisms. And the most novel thing about the PR1's arms is that they're floating, they're gravity counterbalanced. And so if you think about a robot and it's going to be around you, if it's a traditional robot arm like that one, I didn't show you enough of the Carson clip, but what's interesting is Joe Engelberger, who created the company that first commercialized those, he's standing right next to that robot. Right? And he's ducking down, and I'm thinking, man, that thing could turn and just take his head off. Right? It's a scary thing. In the PR1 case, and also in the PR2, they have this gravity counterbalanced arms, and what that means is that there's a spring here holding up the weight of the arm against gravity. Right? The arms are heavy, and so especially if you put the motors out in them and so forth, and if you don't do that, what happens is if the power goes off, the arms go boom, right? And it's like just if your arm fell asleep, right? It just falls down. If you've ever been sleeping and reached your head up when your arm was asleep in the morning and hit yourself in the head, I don't know if you've done that, but I tell you, it hurts. So this, with the gravity counterbalance, the arms basically float, and that's pretty cool with the power off. Let me show you an example of the PR2 now. And the PR2, this is an example that was done by Bosch. So Bosch has one of our robots and in their Palo Alto office. And this is sped up by 20 or 40 times. If you watch in the corner, it kind of tells you. They're doing mail delivery, kind of the classic office task. And notice that nobody's interacting with the robot. Nobody's touching it. I mean, they may take a package from it, but it's basically navigating on its own and moving around through the environment quite successfully. So that's the PR2. And I'll come back and we'll bring out a PR2 in a couple of minutes. But let me show you, let me talk about a little bit the sort of the business model. So Willow Garage is a company that's been around for about 4 years. We got started working on the DARPA Urban Challenge, if you remember that, and didn't actually do that well. We kind of were a late entrant. But we decided to focus after that on taking the PR1 robot from here at Stanford and creating this PR2. And our goal was, let's give away 10 of these, and let's create some software that goes with it. So we gave away 11 because we couldn't decide. And we also had a lot of demand, so we said, OK, we'll sell these things. But this is not a business. Right, this is research organizations around the world number in the tens who can afford a $400,000 robot. It's not something like we're going to put one of these in your home. But what we hope to have happen is that, like in any other industry, we have a business model like that. One time I put this slide up and I had a title business model on it, and everybody laughed. It's a great business model if you can do it. The reality is, we think that it's 10 or 15 years off before you're really going to see robots in every home. But the other reality, and you probably know this, is that you can't actually have an exponential growth curve like that, right? Because eventually you consume all the energy in the universe and it ends, right? So any exponential growth curve actually goes like this, right? And if you look at something like Moore's law, it's actually like this. It's a linked series of curves that each technology, each successive chip technology over time, even from the time when you had, I guess cold chips or whatever you had before the current hot chips, or maybe it was hot boards before that. But every successive technology gives you a little bit and then tapers off, hits its growth limits. Most recently, we hit this and we started going multi-cores, right? You started hitting limits in terms of how fast chips can go. So in robotics, I'm predicting that the same thing's going to happen. And like any prediction, this will be wrong, but I'll try. And so this one we know, right? Roombas came out. They're vacuum cleaning robots that are sort of entertaining and not so great at cleaning. And Roombas came out, and lots of people bought them. I think they've sold like 5 million. And there's actually follow-on. There's other companies that are selling disc-shaped cleaning robots. If you go to robotic shows in Japan, you see just like one after the other after the other. It's amazing that there's so many clones. But they pretty much have saturated the market. Anybody who wants their house cleaned at that level and is willing to put up with that has one. And then there's follow-on products that are kind of similar, but you're pretty much tapering off in terms of the growth. I actually believe that the next technology is going to be what we call remote presence technology. And this is basically due to a confluence of a few technologies. I shouldn't actually put it in the deck. I should have. There's a technology, a robot that we created called the TexEye. And the TexEye is a remote presence device, we call it. It's basically a mobile base, a stick with a screen on top and a camera. And you can basically think of it as Skype on a stick. You're Skyping with somebody, except that on your end, if the robot's on the other side and you're talking through that robot, you can basically drive it around. And you would think, OK, that's kind of cute, except that the experience we have, both internally and through customer testing, is that it actually makes a huge difference. So the guy, we call it the TexEye at Willow Garage because the guy who invented its first name is Dallas. And Dallas lives in Indiana. And he was the voice in the middle of the room for a long time. When you have a conference call, he basically called into weekly meetings at Willow Garage. And he was the guy who was there inside of the Polycom, right? And that means that when you looked around the room to see if everybody was nodding, he was ignored, right? And he doesn't see the eye contact between different people. In other words, it's not a great experience. If everybody's in the room except for you, that's like the worst way to be on a telecon. What changed, he said, I don't like this. Can you get me a laptop with Skype on it? So they put Skype at the end of the table, and that's better. He still can't see the board if it's on the side. And the other board at the other end of the room is probably too far away for him to actually see with the camera. But it's getting better, right? And he said, can we do better than that? Let's get a little, one of these Logitech cameras so I can look around and you can kind of see where I'm looking. And that was a better experience. In order to put that together, instead of sticking it on a laptop, they got a little cart and they put a UPS on it, and they put a computer on it, and they put a screen on it, and they put this little Logitech camera, and now they could push him into the room without having to reboot, right? Because then you could just plug the UPS back in. And all of a sudden it was like, wait a minute, we're a robotics company, right? We can do better than this. And so they took one of the old casters off the PR2. You'll see the PR2 has 4 casters. And they took one of those casters that was sitting on the shelf, stuck it at the bottom of basically an 80-20 rig. If you know 80-20, that's the erector set for adults. And they put a marine battery down there, so basically a lot of power. They put a computer on it, they put a screen on it, they put the camera up there. And all of a sudden there was this robot. Because we have this open source software, they were able to basically describe that robot to the software, and suddenly they had a robot that they could drive around. And all of a sudden, literally over the course of a week or so, they've gone from we're putting this cart together to, oh, we hacked this thing up. Now, they're a bunch of double E's, and they were able to get the power stuff right. I would have probably blown up a few monitors in the process. But the result was, all of a sudden, Dallas is not stuck in the room. He's not stuck. He's not tethered like when he wants to have a meeting, they push the cart into the room. All of a sudden, he has freedom to wander around the office anywhere he wants, right? And so before this, since he lives in Indiana, I had met him twice in the course of about 18 months. After this, I started seeing him almost daily in the halls. Right? I'm walking along to the cafeteria, there goes Dallas. Hey, Dallas, hey, Steve. It's like, it's an interaction. It's interesting. Here's this weird robot like this. But the robot almost becomes invisible, right? Because here's Dallas wandering along, and you see him, you're interacting with a person, you're not interacting with the robot. Now, he's a little bit weird because he turns weird and he makes noise while he goes, but not bad noise, just like bzzz, we didn't super quiet those casters. But he, all of a sudden, he starts coming to stand-up meetings. If he wants to go to a seminar, he reads about a seminar on the internal email list, he can go to the seminar. It's a little bit odd, right? Because you have to accommodate him a little bit. When you're in a robot body, where do you sit in the seminar? Well, you can't actually sit. Where should you stand? Not in front of everybody, because they can't see through your screen, so you're kind of off to the side. But those protocols can be worked out. The result of it was his life changed. And we tried this in a few other companies, and when we pulled back the trial in order to sort of go on to product, people were saying, wait, I want that back, I want that back. So it's a long way to say that. I think this is a next big thing. And there's other companies out there building similar products. I think there'll actually be a market here. After that, I think the ability to act there, the thing that everybody asks is, OK, so you can be there remotely, right? So it's a human driving a robot. We haven't solved AI, and we're not going to for a little while, maybe a long while. So in the meantime, somebody driving the robot is actually pretty cool. And beyond that, we're in a research phase today for some kind of versatile automaton. In other words, a robot that can basically come out and do tasks on its own. And I'll show you a couple examples of completely autonomous tasks that we've played with. This actually might be a good time for me to introduce the PR2, if I can figure out how to turn this on. Let's see, so you can, if you want to see what I'm doing, I can do it on here. Does that work? You can kind of see what I'm doing. So this is a little application. We're thinking about the App Store, but it's hard with the robot that there's about 30 in existence. It's just you can't find a lot of people to write apps for it. There's a bunch of grad students, most of them been interns where we are. But let me bring it out to show you. So if I bring out map navigation, and I'm going to, here it comes. What? Oh, there you go, thanks. And we made a map just in the 10, if you were out here early, you saw the robot wandering around. So we made a map of the stage. I want to thank Tony Pratt-Canis, who's sitting in the front row holding the run stop, because we've never been like where it could fall over the edge before, and it's 450 pounds. So these guys in the front row, be careful. So let's see. So let's see, what am I doing Is this the map, Tony? I'm not seeing the map, which means I probably did the wrong thing. And here comes Tony. All right, I'm going to let Tony play with that while I tell you a little bit about the robot. And he's going to make it drive out. Oh. Ah, there we go. Except that you can't see it. Due to the, so this is one of the things I was going to tell you in the course of this talk, and I'll say it again later, is we need better sensors. Right? Like this camera, it's really hard to get a camera that's even close to what your human eye can do. I mean, if I have a robot on stage, we didn't set it up so you could see what it's seeing. But if you could see what I'm seeing, right? It's like bright lights. It's like the stars. And I think there's a few people out there. There's somebody in the front row I can see. So, okay, here's a map of the stage. And now he didn't do what I was hoping, which is this. See, if you do this, then I know where I'm standing. And if I say place position and I go here and tell it face that way, then is this one of these things about how well Wi-Fi works inside of a big auditorium? I'm not sure. Where'd Tony go? What do you think, Tony? Let me stand. Oh, it's like saying it can't see anything. Is it going to plug in? He's going to push. I give Tony the tablet, and I'll keep telling you about the hardware. Okay. I was just thinking about that. So what I was trying to show you is what you do when you do a live demo. I was trying to show you the latest, greatest, which is we've been using an Android tablet to control the robot, because it turns out, you know, it would be great if you could just have it be speech controlled, but that's a pretty hard problem. Okay, so here now magically, the robot is going somewhere. If I do this, is that? Oh. So a lot of technology going on. So there goes the robot. There's the map. This thing you see right here, that's my podium. And over here, that's that long table. And I told the robot, go in the middle of the white box, because that's where the cameras can see it, and turn and face you all. There you go. So this is PRK. And I'll just introduce you. It's a PR2 robot. It's PRK means we have to give them names somehow, and we're not very creative. And here's a robot. If I put it in the right mode, it'll be even better. So let me tell it to, you know what, Tony, maybe I'll just have you help me drive this. It'll be easier. Because it's hard to drive and talk at the same time is what I figured out. But I go into Mannequin Mode. If I make it a Mannequin Mode, what I'm telling the robot to do is just hold your position wherever I tell you to go so that I can talk about it. So here's the arms. Now it looks like I'm pushing a little bit to hold the arms. You'll notice that, like Joe Engelberger in the Carson video, I'm standing next to the robot inside of its workspace, and I'm not too scared. The robot, even if it was trying to hold position as tight as it could, I could just grab it and move it, right? And that's, again, by design. We've put the motors, even though it's got these massive biceps, they're not actually biceps. They're just a place where there's a fan, I think. But it's got a relatively small motor up here, because it doesn't have to hold, that motor doesn't have to hold the whole arm up. That motor can just hold the payload, which is designed to be about 5 pounds, right? So you're pretty much stronger than it. You can open its grippers. And in this particular mode, what it's doing is whenever I move it to a position, it just holds that position from then on. We call this Mannequin Mode. And it turns out to be nice to kind of show it off. And it's great for taking pictures. Not much else. So so I'll just go top down. This is not standard equipment, although we're starting to put them on. This is an Xbox Connect, Microsoft Connect for the Xbox 360. It turns out, so this is the message for this audience. This is awesome. This comes out of the consumer electronics industry. It's $150, and it gives us 3D point clouds in real time, right? Before that came out, we built this robot. This has 2 sets of stereo cameras, one wide angle, one narrow angle. This is actually a texture projector that puts out a bright red light with a pattern, so that when you aim it at like a tabletop, you can get really good stereo data. Turns out stereo doesn't work real well on objects without texture, right? Stereo is about looking at the same piece of texture from your 2 eyes. Your eyes are really good at it, right? Again, the sensors that we have aren't that great. And so when you have a sensor that's, you know, a little bit not perfect and you can't see all of the the texture in an object. If you don't have texture, you can't do much. And then this is a high-resolution video camera. There's also two cameras in the forearms, which are intended to give you a close-up view of whatever the robot's grabbing right now. Turns out, in hindsight, we should have made those stereo cameras, and we should have put them here. Because what you really want when you're kind of trying to grab something is to know exactly where it is in space, precisely. And you can't quite get that with this. You can kind of get it with this, but you're now at a meter away, and so you have error. This is a tilt laser, which is not tilting right now, but it goes up and down. And down here is another laser. These are laser scanners that come out of the garage door industry or the industrial automation industry, where you basically want to create a light curtain and keep people out. Turns out the way that they work, they send a laser back and forth at 40 hertz, giving you distance information. And so they've also been adopted widely in the robotics industry to help you do navigation. So most common sort of inexpensive robot, and probably the best results over the last from 15 years ago till 5 years ago, was to solve the navigation problem, which means you put down a robot and you want it to drive around without getting lost. And the way they do that is they put a laser scanner, they see the walls, they get a 2D map of the walls, like what you were seeing on the screen there. And in this case, there's no walls, but it was actually making a map of this and the monitors and other things, enough that we figured it could localize. That was odd. Oh, is that you? Oh, there's. I was like, wait a minute, it's doing something else. Tony's telling it to do something, so you can actually see my, switching back and forth. He's actually showing you the video live from this camera on the tablet up through there. It's amazing. So the laser scanners are cool. This one's what's traditionally done in robotics. This one, when you start tilting, it all of a sudden gives you a 3D point cloud, right? Now, the Kinect gives you a 3D point cloud, but not until a year ago. And it only gives you a 3D point cloud in your living room, meaning it's really, really good at couch distance, right, from the robot, because that's what it's designed for. If you go couch distance times 2, it just says you're far away, right? And all those distances beyond the couch are just far. And if you're half a meter within it, it's totally blind, right? So the Kinect has its limitations. Again, it's designed for what it's good at. These lasers are really good out, probably not as big as this auditorium, but easily as big as the stage. Right? They can see all the walls in a fairly large room, and they'll give you distances very accurately all the way around. OK, so that's the sensor suite. I talked to you about the arms. The head's just on a simple pan tilt. And you'll notice this industrial design. If you look at it closely, there's basically this bolt hole pattern all over the top where the Kinect is attached. And the intent is to make it so it's easy to attach other sensors. This robot is not designed, as I said, to go in your home, per se. It's designed to go into a research lab and help people develop the next generation algorithms. And the state of the art of robotics right now is, how can I come over to this table, identify what's sitting on it, and pick it up successfully, and then manipulate it in some way, put it somewhere else. That's pretty much where we are, and we're putting together basic object recognition primitives with basic grasping. And you think grasping is, oh, you just put the gripper there and grab, right? But it's a lot of subtlety about how you actually grab an object. If you think of an object like this one, I can't just grab it here, or I don't usually just grab it here, right? I want to grab, you know, as a human, I'll grab it here, and you can actually do a lot with your hand. You can, with one hand, take it off, right? But that would be actually quite a challenge for a robot to do at this point in time, at least autonomously. And even under remote operation, it'd be challenging, because how do you tell it to do that? And I was using the fact that I have, lots of fingers here. Hands with 5 fingers and humanoid, there's a lot of people who are making them in robotics, and they almost always break, right? If you want to actually use it for a task, it's going to work for 20 minutes, and then you'll re-cable it or whatever you're doing. Again, the state of the art today. In the base of this robot, there are 2 computers. We put 8 cores in each one, so 8 i7 Nehalon chips. There's 24 gigs of RAM in each computer, and 1.5 terabytes of disk in each computer. In other words, pretty beefy, at least for us computers. And when you figure that's 2, that's 16 cores. It's pretty decent. It runs hot, right? So this is my second call for cool chips, right? One of the things that we need in robots is to figure out how to not have 60% of the battery going into the computers and not the motors. OK, let me see what else did I not tell you. So that's pretty much the PR2. Do we have other demos we should show?
You got props. You want to do props?
Oh yeah, I have to do props. Can you? So this is what's it? What? Okay, now it's doing its own thing. This is just a cute thing called props. I wait. Is it doing two-handed? So it wants to do two-handed high five with me, I think. But I don't know when I'm supposed to go. Now? So this is one of these things like, what do you do with your, oh, there we go, high five, right? And now it senses that and it puts them back down. OK, that's cool. You guys are easy. If that's, well, I'll show you some videos later that are really cool. So the other thing about this is the fingertips. I mentioned, here's the gripper, and it's a pretty simple gripper. Inside of the gripper is fingertip sensors. There's an array of about 21 of them. So 15 inside the fingertip and then 7 around the edges. And that turns out to be enough that you can actually pick up an egg with this without breaking it. You can also break it. It's a good idea to put it in a plastic bag. And because it's not cheap, the robot. But you can, so that's pretty much the only touch sensors on the robot. We didn't put, for some reason, bump sensors here, which is typical on robots. It said we're leveraging the fact that we have that pretty good estimate of what's going on from the lasers in terms of the environment. This is just sort of padding, so if you do have to grab it in a hurry, you don't get hitting straight aluminum. But it's just a soft cover. It's not sensors. There are people working on sensors, but one of the challenges of sensors is how are you going to get, how are you going to wire it into the robot and deal with all that data that sort of is not off the shelf. I'll come back to that. All right, so I mentioned this one. Let me show you a video of the robot in action.
Hi, I'm a member of the Willow Garage Pool Shark team, and we just programmed the PR2 to play pool. At Willow Garage, we like to challenge our raw software by doing short hackathon sprints. These sprints help spark new ideas, test our raw software, and most importantly, are fun. Our most recent sprint was a game of pool with the PR2. This required tackling several different problems at once. In order to get the PR2 to use a pool stick, we built a special grip and bridge so that the PR2 could use its wrist to power the stick. Two other challenges were finding the ball and localizing the table. To find the balls, we used the high-resolution camera with a color blob tracker, as well as a casino set of billiard balls that were easier to track. To locate the table, we used corner detectors to find the diamonds on the edge of the table and used the bottom laser sensor with AMCL to detect the legs of the table. Once the PR2 knew where the balls and table were, we could pass that information to our shot planner. We used FastFizz, open source pool physics library by Alone Altman, to check the results of our planned shots before executing them. We began our pool playing sprint on Monday morning. By Friday afternoon, the PR2 was successfully pocketing shots. It even surprised us by making some fairly long shots, as well as shots from difficult angles.
Yeah, see that?
While there's definitely more to improve, our team is excited to see how much could be accomplished in just 1 week. All our code is available on ROS.org in the billiard stack.
See, that's really cool because they did that in a week, right? We said on Monday morning, let's do a hackathon. There was, what, about 10 of them. He's actually a really good pool player, but he can't use the bridge that we gave the robot. But we said on Monday morning, let's do this. And by Friday afternoon, it's pocketing shots, right? Now, I don't want you to think we've solved pool playing. This is not going to show up on ESPN or anything. But it's a demonstration of the power, if you have a good hardware platform and a good software platform, of what you can actually do. Our goal in this is to be able to be a catalyst for moving research forward. So in the PR2 and ROS exist specifically to say, look, in the worst case, this is a graduate student's career, you have to spend the first 4 years putting together stuff that other people have done, building a robot that you're putting together yourself typically, or we're working with a small team, and coming up with the software for all the different components that you need. By contrast, with the robot operating system and the PR2, you start with the robot, you learn how to use it, and then you spend the maybe 4 years innovating, right? And if we can get the robotics PhD students in the country innovating at that pace, we think we can speed things up dramatically and really be a catalyst to innovation. Okay, let me take you back in time for a minute and give you the analogy of where I think this robot fits in history. And I'll go back to this computer, which you may or may not recognize. This is an Alto computer from Xerox PARC, which was built in 1973. The first bitmap display, Windows, mouse, pointing device, basically all the things that you eventually found on a Macintosh, I guess Elisa first and then Macintosh and eventually Microsoft Windows, were on this computer in the 70s, right? So they started with the hardware that could support it. They actually invented the Ethernet. They invented the laser printer, all these things designed to do the office of the future. Very exciting time, right? The computer wasn't actually that big. It was actually, hey. Oh, I thought I had a, all right. The computer actually, there's a small refrigerator down here. It's like in this screen about this big. But it was so bad that at Xerox PARC, they didn't actually put the computers in people's offices because they heated them up too much. And so they created a server room and basically ran coax all the way around the building. But this is what I think of as kind of the PR2. The cost is actually basically the same order of magnitude. In today's dollars, the Alto costs about somewhere around $200,000. You can get a version of the PR2 for $200,000. And lots of interesting stuff got developed on it, but it wasn't the thing that took off, right? The thing that took off was, not this one either. The thing that took off, I have that computer, the PET. That was my first computer, but the Apple, now I went backward. That's what happens when you do animation. So the PCs that came out, right, these were the computers that really took off and people started buying. They didn't actually do much. This is an Apple II Plus. The Apple II didn't even have a shift key, right? So you thought, here's a computer for word processing. What they actually thought was, oh, maybe this will be useful in the home. Let's sell a recipe application, right? And nobody was fooled, right? Nobody's going to buy a $2,500 computer to do recipes, right, when you can get a $15 box. And actually, Honeywell tried that in 1969. They had a computer like that. In robotics, we're looking for now is the Apple II, right? It's not going to be the perfect robot, but something that can do kind of what this robot can do, maybe on a smaller scale. And I think that's going to come out, my prediction again, probably in the next 5 to 10 years, hopefully within 5 years. We'll see some kind of small robots that actually make sense, that people are actually buying and saying, hey, I can get this to do a few tasks around my home. That's what we're looking at now. What are the technical challenges of doing this robotics? Human-robot interaction is a big one. You can see how much trouble I'm having interacting with the robot while talking at the same time. But it's a big challenge, and there's just lots of different aspects to it. I talked to you about the way that we do remote operation. There's both sides of that interaction, right? You can be interacting with the robot the way that I do with Dallas, or you can be interacting with the robot the way that Dallas does with his surrogate in California, right? Either one of those is possible. Mobility has been a challenge, although it's one that I think is pretty well under control now. The hardest thing about the PR2 is it's designed with wheels, and so getting into Memorial Auditorium, which is marginally ADA compliant, I guess it's technically ADA compliant, must be, and we got in here somehow. But it's not easy, right? You can't bring it up the stairs with you. But navigating around it through space is actually one that's pretty much solved. Manipulation is one that we're on the cusp of, right? There's a lot of work going on there. It's not solved yet, but it's getting solved. Perception is a really hard problem. Perception for robots, making sense of the world is really tough. And I don't know if you noticed it went by pretty fast in the pool playing video, but what Tully was saying is we used the diamonds on the top of the table. So we had they made a custom detector to find those diamonds so that they could say, okay, now we know where the diamonds are. They used the laser to figure out where the legs of the table were. And then they know the structure of the table. They assume it's not going to change. And using that, they can pretty much infer where the bumpers and the holes are. And then they actually changed the set of balls out because the typical balls with the numbers on them, they're actually harder to see. And they only had a week, so they said, well, let's just get a billiard set, a sort of standard set where they're just 2 colors, and we can track those easier. So you'll notice when you see robots solving perception, or people solving robot perception problems, that there's often fixturing or helping in some way. I had an intern show a really, really cool demonstration of some object recognition technology in our conference room, and I turned on the lights, and suddenly it didn't work anymore, right? Because you optimize for some situation. So lighting and things are really complicated, and I don't have time to go into them all. And the last one is complex real-time control. So one thing about the PR2, it's holding position right now, but it's basically, it has a force control mode, but it doesn't have really good force sensing. So when I do this to the robot, it knows, it doesn't know anything. Its sensors can tell it, or its software could detect, if I be careful, that I've moved it down like this, right? Because there's an encoder here along with the motor. So the motor spins, but there's an encoder that basically counts how many times that motor's gone around. And so to within a degree or so, it knows exactly where that joint is. And as I make a lot of joints move, it knows where all the joints are. And so the visualization software that we have for this could actually show you, while I'm doing this in real time while it's running, you would see on the visualization software that the robot's moving in that space. And so it knows in that sense where it is. But it doesn't detect forces very well. So if you want to do a task like wipe off the table, that's more challenging because you don't know how much force to apply in a constant way. Or write on a whiteboard ends up being a kind of challenging task. So we're looking at force torque sensors that are very small. OK, I'm running out of time. So let me show you one more video of other robots, personal robots today. These are all robots that are running the robot operating system, ROS. This is the PR2 playing with or without you, but I don't have the sound on this. Here's a robot in Munich flipping pancakes. Together with the PR2, they actually got the mix out and served pancakes. They served 4 pancakes in an hour. It's really impressive. This is actually really, really impressive until I tell you the secret. Right? It's running inside of a motion capture system, so the perception's all external to the robot. This is a robot here at Stanford. That's Morgan Quigley building a robot arm out of plywood. By the way, the PR1 was out of plywood as well. Here's a couple robots. This is a robot from Germany dancing with the PR2. Here's a robot that's designed to go inside of gutters. This is a robot that also is coming out of Stanford and Google cars. There's a bunch of different car projects after the DARPA challenges. It's not exactly a robot, but it's an instrumented board, and the accelerometer data is going straight into ROS. This is a TurtleBot. This is a $1,000 robot. If you want to play with robotics, you can get one of these now. It does 3D sensing and mobility. It can do mapping, kind of like I did with the PR2. And this is a robot at Georgia Tech that's kind of a hand-built. Actually, it's an arm from Mecca here in San Francisco. This is a typical kind of robot, servobots. So lots of servos. If you go to Japan and look for robots, that's what you see. And here's a very early PR2. And there's a robot at Stanford here opening a door. So you see kind of the things that are going on. Let me spend the last few minutes of the talk giving you my wish list. So for all of you, as I said, this is my first time at Hot Chips, and so if I make assumptions about what you can do, I apologize. You can just ignore it. But if you can solve any of these problems, it'd be great. Let me know. So here's my wish list. First thing is, robot batteries never last long enough, right? And so you may not be battery people, but if you're not battery people, then you're consuming my battery, right? And so we need cool chips, and I mean that. We need robots that give me, if you can give me infinite computing for no energy, I'd be really, really happy. In the meantime, lots of cores will be great, and as little power as possible. You can hear I don't know if you can hear it, the fan on the PR2 is fairly loud, and that's because it's basically trying to cool all those Halon chips inside. So the second thing is, shared memory compute. So if you do have lots of cores or lots of processors, somehow this can also be, shared memory is what the perception guys asked for. So I went around my lab asking everybody what they wanted from you all, so you can help them out. But perception and planning take most of the traditional computation. And perception in particular, you want to do it in real time, right? I saw a really cool demo of pedestrian detection maybe 10 years ago, where the robot could or the camera, it was just a fixed camera, but it could see somebody walking, and then they walk behind an occlusion, and they walk back out the other side, and it continued to track them, and it was great. And I said, when I started Willow Garage, I went to the person who had done that work, and I said, can I get that algorithm? And he said, well, yeah, but it runs in like, if you take a 1 minute of video, it's going to take 60 minutes to process it. I'm like, well, that's not going to work, right? The robot can't watch the pedestrian go by, or a robot car can't watch a pedestrian go by and then 60 minutes later say, what's going on? So we need real time. Fast communication. So communication ends up being really important, and another way to keep the batteries working on the robot and letting the robot run for longer is to push the computation out into the cloud, right? Which is a great idea in theory, and may work on a robot that doesn't have too many sensors. This robot's got, if you count the Kinect, 9 video cameras and 2 laser scanners, and those things put out a fire hose of data, right? And if you put that on your Wi-Fi network, you're not going to get that data off by itself, much less everybody else's data if you have other robots in the same room. So the same problem you have when you go to a conference and everybody wants to use Wi-Fi is multiplied with robots that are trying to take lots of video if you want to process it in the cloud. On the other hand, snapshots and having people in the cloud actually works. GPUs, and I had to put especially with Ubuntu support, so everybody says, we got great GPUs, but they always only work on Windows. And that's great for PCs, but for Linux embedded is pretty much what goes on in the robotics world, and that just makes a lot more sense for us. And wiring is a real pain in robots, right? So you look at this point. Let's take these sensors at the end here, or the motors that are in the end. It's going through a whole bunch of different joints, right? And the PR1, you probably didn't notice, but the PR1 has this big bundle of wires that ran from one joint to the next because they avoided the internal wiring problem. The PR2, Keenan Weierbeck did a really nice job of working the wires through here. And there's a slip ring, so this is something you can't do with your own arm. It's just, keep turning it all the way around, right? But the robot basically has continuous rotation joints there, both at the wrist and here. And that means you have slip rings, right? It means you have wires going through those slip rings. That means as a manufacturer, you spend a long time trying to make sure that those slip rings are going to be robust and it's going to work. Is there some way we can reduce the data going through? We've done a pretty good job in this design with a bus called EtherCAT. Right? EtherCAT is a real-time variant of Ethernet. And it turns out we've discovered that if you want to get electrical signals through slip rings, you send them through Ethernet. That works really, really well. It's really robust. USB is OK, and just say no to FireWire, right? Because it doesn't go through slip rings. It's too noisy. So wires are failure points, and connectors are failure points. In fact, the biggest problem we've had in terms of reliability on this robot was in the Ethernet cables inside, right? Just the connectors. We got a batch where all of a sudden they're not quite working right. Hobbyist access. So one of the things, if you think back of cars history, think about when cars became really popular in the 50s, right? And my dad was into tinkering with his car, right? Lots of people in that time were making hot rods or creating or mussing with their cars in a way that you just can't do today, right? You don't get your Prius and think, oh, I'm going to go, soup it up some way, right? You trick out the wheels, but you don't go try to mess with the engine because it's so integrated. But there's an important tinkering phase there. And if you go back to the early days of the PC, there was an important tinkering phase. People would open it up and do their own thing. You have the homebrew computer club, right, where the Apple came out of. I just spoke 2 weeks ago at the Homebrew Robotics Club, which is the modern equivalent of that, thinking that, hey, the next generation is going to be this. And what hobbyists need is the ability to take those, the latest chips, the cool pieces, and put them together in some interesting way. And it's not easy to just take, if you think that my market is the place, where I make 1 million chips for somebody from some industry, think about if it's possible to make those chips available with an API or some other development kit for hobbyists, because that's how we get things into robotics. Robotics today is in the early stage of that exponential growth curve, and we're the poor stepchild of the other industries, right? We use a 3D sensor that's made on video games because they can sell 10 million of them, and we can get them cheap. We use sensors, laser scanners that come out of the garage door industry because they have a need for them, and they've created them. And once they're created, we can leverage them here. We use off-the-shelf motors that have taken a long time to evolve to where you can just buy them. Specialized processors, there's a whole bunch of areas where I mentioned the stereo inside the fingertips. Right? That's a really important place. Basically, close-range depth sensors at the end of the arm. Has to be light, has to be small, and would be a great thing for robots. And that would work on both big robots, mobile robots like this. It would also be valuable in factories which have thousands of robots. And if you believe Foxconn, there's going to be 1 million robots next year. Another thing is thinking about what can you put on a chip. So if you can put a sensor, an image sensor on a chip, can you put a textured light projector right next to it? So the Kinect works, gets 3D data by putting out an infrared pattern on the world and reading it back and computing the distance based on that. So is there some way to put structured light on the chip right next to the camera, or maybe 2 cameras, in order to really get good data close up? Actually, so any technology designed for robots is welcome because, like I say, all we get in robotics is hand-me-downs. And the last thing I'll just say one more time is cool chips. Let me end with 2 quick videos, and then we have time for questions.
Have you ever really wanted a beer, but you don't want to stop working?
Oh, I just like...
At Willow Garage, we've solved this problem. We built a web interface that has a menu of a number of different beers that you can select from. Once you select the beer of your choice, you can place it in the beer bucket and then select a location of your choice for the robot to drive to. Once those 2 things are completed, you simply click the big Beer Me button and the robot comes to you to deliver your beer. In this process, the robot goes to the fridge, detects the handle of the fridge and opens it, looks inside of the fridge and uses its cameras to detect what kinds of beers are available. If the beers you've selected are not available, the robot will inform you that your choice is not available at this time. Otherwise, the robot picks the beers that you've selected from the fridge, puts them in the cup holders mounted on its base, and delivers them to the location that you selected. Once the robot gets to this location, the robot waits for a face to appear in front of it. If your face appears, the robot looks directly at you, and you know it's okay to take the beer. The robot won't release a beer unless it sees a face in front of it. We also got the robot to use a bottle opener to open beers, so even if you don't have a bottle opener on you, the robot can crack it open for you when it delivers it. Oh, cool. All right.
So you'll remember, this is an 8-person team, and again, 1-week project. You'll remember that the PR1 cracked open a beer too, right? But that was under human control. This one, the whole process was completely autonomous. So they spent a week programming it to do all the tasks on its own. It doesn't work in your fridge, in your house probably, but it's designed for, in a week, we tuned it for 1 refrigerator. The last one I want to show you is where I think is a really, really compelling use of a general purpose robot like this. I mean, you could say, well, why do I really need a robot to bring me beer or play pool for me? Those aren't really compelling applications. This last one is work that we've done with a guy named Henry Evans, and I'll let the video.
Cousins, and I'm excited to tell you about a new collaboration today between Willow Garage, the Healthcare Robotics Lab at Georgia Tech, and Henry and Jane Evans. We call this project Robots for Humanity. When Henry was 40, he suffered a brainstem stroke, which left him unable to move his limbs or speak. Jane, his wife, helps him with most of his daily living tasks, including eating and speaking.
R-O-C-B, robot.
After extensive physical therapy, Henry can move his head and has limited use of 1 finger. This allows him to virtually move a mouse with his head. He can surf the web, correspond using email, and write documents. Henry saw a PR2 on CNN and wondered whether it could help him. We have been working with him ever since to develop tools and interfaces that allow him to control the PR2 and to use it for his daily activities. It is extremely important for Henry to be able to do things for himself, both for practical reasons, but also so that he is in control of his own world. Even simple tasks, such as scratching an itch, are important. Henry estimates that 2 or 3 times an hour he gets an itch that he cannot scratch himself. Earlier this year, He moved a PR2's hand near his face, and by moving his head, scratched his own face for the first time in 10 years. Henry hates being shaved, so we tried letting him shave himself with the robot. He was successfully able to shave his cheek by moving the electric razor to his head and moving his head around. We're actively working to let him do a more complete job. While these are small steps, they demonstrate how we can use robots to give physical assistance to persons with severe physical disabilities. The interfaces we have developed allow Henry to interact with the robot's autonomous capabilities, such as navigating around the building, avoiding obstacles, and grasping and manipulating objects. He has already made the robot put objects in a drawer from another room. All the tasks that you see in this video are performed by the robot under Henry's direction and with his input, through interfaces developed by the Robots for Humanity project. Robots that complement human abilities are extremely valuable, especially when they allow us to do things we can't do by ourselves. Our goal is to enable robots in homes to help people like Henry, and this is just the beginning.
So with that, let me wrap up and take any questions. Thank you.
If you have questions, please come to one of the microphones and state your name and affiliation.
Todd Besnick, Quantum. I'll ask the obvious question. Can you leave the PRK here so we can look at it during the break?
Oh, good question. I think it would maybe. Let me see if we can. We were going to head back, but I'll try.
Hi. You talked about the need for better vision, if you will. Does that actually, and then you also talked about the fact that a lot of the computation is done to process, to perceive things. Is there some kind of relationship if you get better sensing? Do you have to do less processing, or?
Sometimes, and sometimes it's the other way. The 5-megapixel camera on the head hardly ever gets used because it puts out so much data that it's just a pain. And so you have to do more processing to kind of downsample it and deal with that data. So it's a better sensor, right? But it's harder to use. So I think if you come up with a sensor that has processing embedded, a stereo pair that has stereo processing there that puts out a point cloud directly, for example, it may actually be less work for the main CPU. And so there's a trade-off. It's actually a pretty complex design space. Yeah, thank you.
Thank you.
Hi, Brian Case. You said that you could use infinite compute power, and maybe you could restate how much is actually in the current version, but then could you also talk about how utilized that hardware is,
Sure.
and what are the sort of increments? Like if you could get 10x, you can do something, or do you need 100x to get to the next increment, and so?
So inside the computer, there's altogether 16 cores, i7 cores, and they get utilized. We can do simple things, just use half of them, so 8 cores. We can also easily saturate the whole thing. So there's a lot of algorithms that you want to run. Imagine, you have, especially at this point in the history of robotics, you have lots of different algorithms to detect things, and you don't have one good solution for how to do object recognition. So what you want to do is run, 20 algorithms in parallel and see, what they're voting on in terms of what's on the table. We can't really run that right now, so we tend to saturate it.
So kind of like Watson, where you vote, you do all kinds of things.
You can, yeah. I mean, right now, again, this is for research, and so we've lots of different algorithms running there. I know when we run the navigation stack, so it's navigating around and processing data, that consumes most of one of the computers, right? So just that basic task. And then if you're trying to actually do a task while you do that, let's be a security application and try to figure out whether somebody's an intruder, that can easily take the rest. The other thing is, as you move the arms, that's a planning task. And I mentioned that planning is hard. It turns out it's exponential in the number of degrees of joints on the arm, so degrees of freedom. And so these are 7 degree of freedom arms. You can't actually compute that, an exact solution, in a reasonable time. It's NP hard. So what you end up doing is doing stochastic algorithms and trying to approximate a path. And every once in a while, the robot will go like, this to grab something. But that's the best path it could come up with.
And just one final aspect.
Sorry, we have a few other folks in just a couple minutes. Sorry, just one question per person. Sorry, please.
Hi, Koji Suginuma from Nihon University. So talking about your beer and refrigerator demonstration, did you use any marker in the home and refrigerator, or no marker completely?
In this one, there were no markers. Yeah, so we didn't instrument the environment in any way, except that we had built a map and we told it where the refrigerator was. So it knew about where to go, but then it has to detect the handle and then open it. And that technology is actually getting better in terms of once you know where the handle is, being able to manipulate drawers and doors and things like that.
Is that SLAM-based map?
It's a SLAM-based map, yeah.
Okay, thanks.
Yeah.
Okay, 2 more quick questions, please.
Michael Sherry from UC Berkeley Extension. I was wondering if the charging infrastructure for the robot has any similarity with the charging infrastructure for the electric vehicle.
I think there is some similarity. I'm not that familiar with the charging system as a whole. I know we built our own custom power board, and we've got 2 stacks of laptop batteries in there, which is basically the same as in a Tesla, right? Except they have a lot more. And so we're basically trying to charge all those in parallel. Yeah. And the thing, if you're ever designing a robot, make it so it doesn't pull all 20 amps out of the wall. That's one thing we learned.
Okay, last question.
Amitabh Menon from Qualcomm. In terms of your compute utilization, it'd be interesting to know where you're spending most of your cycles, what classes of algorithms are eating up most of your MIPS. Secondly, are you doing everything on those homogeneous platform, or have you used any offload engines at all?
So the answer is to the second one is yes, we've done some offloading to GPUs, and there's a little bit of processing going on in the motor controller boards, but not very much. Most of the work has gone on the homogeneous computers, and most of the compute, again, goes to perception algorithms and to planning algorithms. There's the other stuff that's running is there's controllers running for all the motors, whether they're trying to do effort control or whether they're trying to do position control. So controls is another whole area, but on this robot, perception and planning take most of the CPU.
So for the perception, I mean, you mentioned that with the cameras you tend to borrow from other industries. Have you used sensors that are currently being developed for the auto industry and security industry to do image recognition? And
we haven't tried those at Willow, but other people are playing with whatever sensors they can get a hold of in the robotics community. Yeah.
Okay, very good. Let's thank our speaker.
Thank you very much.